Yeah, so this talk is about this data set that I did not collect, but I've been obsessed with since it came out in 2017, because it had some really cool results, but sort of like no mechanistic explanation for those results. And I've always been wanting to try to find what that explanation is, because the data set used GPS tags to record the exact trajectories of all of these homing pigeons. So it seems like there's a lot of tantalizing data out there to analyze. So yeah, these are homing pigeons. They live in this spot in England, outside of Oxford. And then the researcher, Taka, drove some of these pigeons about 8 miles away as the pigeon flies, and then released the pigeons from here. And then because they're homing pigeons, they knew how to get home eventually. So the experimental design was pretty interesting. It consisted of what they call generations, but they're not generations. There's, yeah, you'll see. So the first generation, they took a bird and flew it 12 times. So over time, it sort of like gets better at finding its way home. And then the second generation, now that bird is considered experienced, and then it's paired with another naive bird, and then they're flown an additional 12 times back home. Generation 3, they retire this orange bird. This red one has now become experienced. It's paired with a naive bird. They fly 12 times, and so on for 5 generations. So in total, there's 5 birds represented across one of these chains. And each bird is flown a total of 24 times or 12 times. So that's like generally the situation, and it mirrors sort of like cumulative culture experiments done in humans. In addition to this, there's 2 control groups. One was a solo control group. So they took a single bird and flew it 60 times, so the equivalent of all of this, but just alone. And then also a pair control, where they took 2 birds and flew those 2 birds 60 times. And so the solo control, so there's a single bird flying by itself over and over again. This is what the trajectories, this is like an example of a trajectory over these generations. So it has some like idiosyncratic trajectory that it takes home, that it's like quite consistent over time. Pair controls, there's more variation across generations, but I don't know. I mean, this is one example, but you can squint and there's, I don't know, not really a strong pattern there. But with experimental condition, for this example, you see a really strong pattern where across generations, it gets progressively straighter. And then they quantified this, so using this measure of route efficiency. So that's the ratio of the total length of the actual flights divided by the shortest possible length, which is the beeline distance. And so if route efficiency is 1, then they flew like straight home. And if route efficiency is 0, then it took them like infinitely long to fly home. So there's the cross generations, and then for each of the 3 conditions. So specifically for the experimental condition, at the start of a generation, the flights got bad because the new bird started flying with the experienced bird. But then over the course of the generation, those flights improved. And if you just look at the last flight of each generation, you see a significant increase in the route efficiency for the experimental condition, but not for the solo or pair control. So that's that paper. I wasn't on that paper, but I thought it was a really cool result. And I was really curious to know what the mechanism driving this result is that allowed the experimental condition to improve, but not these control conditions. So people in my lab have been working on this, specifically Shabik, who's my PhD student. He's in his 3rd year now, but also Fritz has contributed to discussions. He's my postdoc. So yeah, basically we want to explain this phenomenon. So the first thing we did was try to explain this. So like within a generation, can we explain how a pair improves the efficiency of its flights? And so maybe just for more intuition, here's a little video of a pair of birds flying home together. The pink bird is the experienced bird in this case. The blue one is the naive bird. And yeah, it just might be interesting to watch like leadership, if they're pushing each other or pulling each other. Are they flying close together, further away. Just good to watch data in action. It's not as beautiful as your videos, but that's all I got. They do, yeah. Generally, we throw those away. It's pretty rare, and it tends to happen like in the first flight. So if it's like a naive bird, an experienced bird, the naive bird might just go off randomly, and the experienced bird will be like, whatever, I'm just going to go home. So yeah, it's like early flights that tend to happen.
Do they ever get attacked by predators?
Not that I know of in this data set.
Yes, they do.
Yeah.
Dora sometimes throws them up, and there's a whole pile of feathers around where the
Yeah,
raptor has found the release
Oh,
zone.
no.
We had this when we were working with pigeons. They would absolutely annihilate it because the birds of prey figured out where we were releasing them from, gathered there, and
Really?
we lost around a third.
Well, there's an airport here. There's a couple towns. So there's a lot of, it's not just like open space. There's a lot of stuff going on. So our first intuition for analyzing this came from the discussion section of this paper where they said, we proposed that the improvement was due to information pooling, allowing birds introduced in each generation to contribute novel innovations. Pigeons are capable of learning solutions produced through collective intelligence. And then maybe most importantly, pigeons are capable of evaluating the payoffs of their performance such that when errors do get added by naive individuals, these innovations can get pruned on the basis that they lead to worse performance, whereas those that lead to better routes are kept. So, these were their hypotheses, and they seem pretty reasonable. So our analysis started there. So we assumed at first that, the naive bird somehow generates noise in the flight path, and sometimes they might accidentally discover better trajectories. They need to somehow recognize that that was better or worse, and then preferentially retain the better ones. And so we thought that leadership might be a good way to encode sort of quality of routes and also assign responsibility for remembering different routes. I want to invite you to not pay too much attention to the next few slides because I'm going to describe some stuff that we spent months trying all this stuff and it didn't work. So if I don't want you to put too much mental effort into understanding all of these methods. Okay, but leadership, there's lots of ways to measure leadership between animals. We just took a very simple one of the bird that tends to be in front tends to be more of a leader at that moment. So this one, the blue bird would be more of a leader, and if they fly side by side, then there's no leadership in this moment. So this is the first thing we did. We were trying to look to see if birds can adjust their leadership in response to the performance in that flight. So if you imagine here's some flights, and we can measure leadership of bird one. So bird one's more of a leader than bird two in this flight, and they got some kind of route efficiency. Then in the next flight, say by random chance, bird one increased its leadership, and that also increased the route efficiency. Then perhaps if the birds are smart, they're like, oh, you took the lead and we did better, so you should lead more. So in this prediction, we would say that in this case, bird one would increase its leadership even more. And conversely, if one bird took more leadership and it led to worse performance, then perhaps that bird would get punished with less leadership over time. So that didn't show anything. But we were like, okay, well, maybe it didn't show anything because we looked across the entire flight. But if you look at these flights, there's a lot of stuff going on, sort of microscopic stuff. And so maybe one bird is taking leadership here, but then the other bird takes leadership here, and then it switches back, and then it switches back. And so maybe averaging across the whole flight just washed out any signal. So then we subdivided the flights into different subsets, and then tried to do that same analysis for each subset. But as you might guess, nothing came out of that. And then we realized that there's a lot of noise from flight to flight, so maybe they're not being so precise. So this is one example of 4 sequential flights. So this bird did okay, and then in the next flight, flight 9, they flew basically perfectly straight home. But then flight 10 and 11, they again sort of went off axis. So they're not so precise in retaining previously discovered routes. We did a lot of analysis with landmarks, so they all kind of converge onto this part and they fly home. Like I said before, this is airport and they follow roads sometimes, they go through these towns. There's a lot of like structure here, and we try to do a lot of analysis to try to like identify the important landmarks, which nothing came of that. And then we thought this was cool. So in the original paper, so when you release the birds, they do just crazy sort of like flying around before they start going home. And so the data sets cut out this looping, but we thought that maybe the looping was important and interesting. So like maybe they like do a looping to like get information and communicate with each other. And then once they like exit the sort of like initial area, then maybe it's sort of like more just ballistic flight home. And so maybe like all of the route efficiency is like determined by up here. And nothing came of that. Okay, so now real stuff. But that was like months and months of effort. So instead of trying to understand like within a generation, how do these flights improve, we took a broader look and try to look just from generation to generation. Can we understand how this pattern emerges? So in this part of the analysis, we assumed a few things. So we assumed that each bird has some like inherent preferred routes. So again, if we look at this control, the solo control, where they flew them like 60 times, they kind of take the exact route home every time. So we assume that if you flew a bird by itself, it would find some idiosyncratic route and then take that home each time. And then when you put a pair of birds together, they take some weighted average across the two preferred routes using some strategy. And so the key is like, what is that strategy if they do that, and can we identify it? And so we devised ways of interpolating across trajectories, which kind of was fun for a while and lets you like make cool stuff. But the point is, like, if you have two trajectories, we can just interpolate to any degree. So like one is more of a leader, the other one's more of a leader. And so we have a method to do that.
Wait, so how exactly are you doing that interpolation?
So yeah, so so if these are like two trajectories, we break them up into say like 1,000 points, and then we just take a weighted average. Yeah, I thought it would be harder, but it seemed very reasonable. Yeah, so you have an experienced bird and you have a naive bird, and then they do some weighted average across those 12 flights. And then at the end of the generation, this naive bird has become experienced, and instead of its innate preferred flight, now its preferred flight is the weighted average from their shared flights together. Then they carry on that one into the next generation, and so on and so forth. So that's sort of like the scheme of like the simulations that we're gonna do. And so yeah, the key is, you know, we assume they're taking some weighted average according to some strategy, and so we have to like write down a list of reasonable strategies and see to what extent do any of them sort of like quantitatively or qualitatively match the results from the experiment. The problem with this is that we don't actually have access to the preferred routes of the experimental birds. Like the birds, except for the generation 1, all the other birds flew together, and so you don't have access to what their individual preferred route was because they were never flown by themselves.
Had they performed the route before?
No.
So they were completely naive.
Completely naive, yeah. But we do have this solo control group. So there was 9 birds here, and they were flown by themselves. And so we did the simulations on this solo control group, which we ignored for a long time before we realized how valuable this could be. So we generated sort of like simulated artificial chains of birds using the solo control. So we know the preferred route of each of these birds, and then we can simulate them flying together in pairs, and then get some route efficiency at the end and compare the distribution of route efficiencies from the simulated chains to the experimental chains. Okay, so we just sat down and wrote down a bunch of strategies, which I will list, and I'm curious to know if they're reasonable to you or if you have like other ideas of other strategies. So strategy 1 is the most basic one. They just average their routes. They don't know who's better, they don't know who's more experienced, they just average their 2 routes. Strategy 2, the experienced bird uses some like fixed weights, and when we calculated the weight that's that's optimal on average across all 5 generations, but there's some like fixed weight that the experienced bird always uses. This requires knowing that you're experienced and or inexperienced, and you kind of assume that sort of like evolutionarily for some reason they tend to fly for 5 generations, right? This is like a choice that the experimenters made, but in real life we don't know how persistent pigeon flocks might be. Strategy 3, the better bird uses a fixed weight. Again, we figured out the one that's optimal on average across all 5 generations. So again, now this requires you to figure out who has the better or worse preferred route, and then you pick your weight as a function of that, and also this assumption of 5 generations. Strategy 4, the experienced bird uses a weight that's optimal for that generation. So we like found the optimal weight per generation, and we assume that the experienced bird knows what generation it's in and can apply the appropriate weight for that generation. Strategy 5, again, you know who's better and who's worse, and the better bird just like takes full control. It's like, all right, I have the better route, just follow me. And then strategy 6 is the most complicated one. So they have their preferred routes, and then somehow they can test out all possible social weights, and then they find the one that like optimizes route efficiency for those particular routes. That seems pretty hard to do, but like that would be awesome if they could do it. Did I miss any that are obvious to you? Okay, seem reasonable. But yeah, there's a variety of cognition required, right? Like this one, you just do whatever. You don't need to know anything. Some of them you have to know that you're experienced or naive. Some of them you have to like figure out who's better or who's worse. This one you have to do, some like active comparison across routes. Yeah.
If you're looking for another strategy, one would be that they sort of cling to their own route depending on how variable it's been in the past. So you've got if you're doing the solo ones, usually the birds that are sort of most fixated on their route tend to be more leadery.
Yeah, right, yes. That's was it iScience paper or something?
I think it's been shown in a few places.
Okay, yeah, that's true. Do you have a question?
So I'm just a bit confused in both kind of strategy 2 and strategy 5. I thought from the way the experiment was set up, it was always clear which bird is experienced and which is naive. And so if I were to do strategy 5, it would feel like after the first generation, you've immediately converged on the optimal route, because like you just keep, the naive bird just keeps kind of swapping, just keeps adopting the experienced bird's route, and then this just goes on from generation. So what am I feel like I'm clearly missing something, but I'm not quite sure.
What do you mean it's obvious who's the experienced one?
No, I thought that perhaps it was just from the way you described the early experiment, but it seemed like when you were letting the 2 birds go, one had gone before and the other had not.
Yes.
So one knew the route, one knew where they were going, and the other one did not. Maybe I'm kind of.
It's clear to the researcher who's experienced or not.
Exactly.
But is it clear to the bird? Like.
But if the bird didn't know where to go, no. Maybe I'm missing it.
Oh my gosh, so many slides. Here. Right, that's like immediately, so like they just left the start point, and immediately, they're kind of flying side by side. It's not clear that the experienced bird is like taking the leads a lot. Right. Yeah. It's an interesting question.
I guess I'm just assuming that there's a clear target end goal, and yes, I'm clearly missing. So.
Yeah, it's like it's an interesting question of like to what degree can animals signal confidence, and if they can, to what degree does confidence correlate with ability? And so it's not clear to us whether there is like some signaling here of experience or not. Like sometimes like the naive bird just like takes off in some direction. So like, is that confidence or is that confusion? It's like an open question. Are there any other questions? Oh, yeah.
Yeah, don't want to derail you too much, but another strategy would be like a class of models just for which WE is greater than WN. So instead of them equaling 1/2, just like there should be some class of models where the experienced bird's always getting a bigger share of that average. Right?
Yeah.
So like that should make some different predictions, I assume.
How do you figure out what that is? Like, do you just draw it from some distribution?
I don't think, I mean, it may just be a class of models that best describes the data. It may not even matter whether you can fit what the value is, but just there may be some subset of models for which you just, it's clear that whatever WE is, it's probably bigger than WM.
Yeah, right.
So each naive bird that comes in just has a smaller influence on the average than the experienced bird.
And there's also, you could do like these strategies plus noise, right? Like what's the odds that it's like doing exactly the optimal or something? So you can add noise and kind of like degrade the performance of each one as well, which is kind of related to that, I guess. Okay, so these are the results comparing each of the strategies to the experimental data, which is in black, and this is root efficiency across generations. So I think one thing that stood out to us immediately was that the real pigeons are like not actually doing that good. And there's two strategies that seem to be approximately similar to the data. Are there guesses to which ones those might be? Equal weighting. Yep, that's one of them. The other one was the better bird takes full control, which is actually the worst strategy. Like it sounds like a good strategy, but there's no averaging involved. And it turns out like averaging is really good because that gives you like wisdom of crowds and like averages away errors. So if you just always follow the better bird, that's actually the worst strategy out of the ones that we considered. But then, yeah, the blue one is simple averaging. They just take just 50-50. So those are like our two candidates based on root efficiency. But we can also compare these strategies on the social weight of the experienced bird or the naive bird, whichever one. And here for the experimental data, we used leadership, like average leadership, as our proxy for social weight. And so it seems like there's no pattern between whether you're experienced or naive and what social weight you use. So it's like 50-50, which simple averaging would predict, but none of the other strategies would. So it seems like they're just blindly averaging their preferred routes and not doing anything special at all. Like it seems like they don't know who's more experienced. It doesn't seem like they know who's better. They can't really like learn anything. They just like average. Which is okay. It's like pretty good, right? Like I said, averaging can lead to a kind of wisdom of crowds. Like if one dude flies way over here and is really bad, then like statistically you might also get someone over here in your chain, and then you can average it out and get a pretty good result. But it's a weird wisdom of crowds because of the way they're doing this chain. So if you look at the very end of the experiment, if they're splitting their route 50-50, then this like very last naive bird is making up a full 1/2 of the sort of like combined routes, whereas this experienced bird, which encompasses like all of these other birds, makes up the other half. So it seems like this naive bird is like overrepresenting its own opinion across the group. And then the other half of the routes is made up of these two birds, which is the experienced bird and the naive. So this naive bird is making up a full 1/4 of the combined routes, and so on and so forth. And so it seems like this kind of like chain design and the fact that they split their routes 50-50 leads to this geometric sort of like forgetting of previous paths, where like the first bird contributes only like 1/32 of the total combined path. So that's not great, because for like maximum wisdom of crowds, you would want like equal representation across all of these birds. And it turns out one of our strategies does match exactly to that sort of like typical wisdom of crowds, where each bird gets equal weights. And we see that, I think it's the either yellow or brown one. I think yellow one. And so that one does better than simple averaging. But then I wanted to know, can we quantify how much worse the simple averaging does compared to the straight wisdom of crowds? So the experimental design basically has a group of 5 with this kind of like social weight distribution. And we know it's better than, or it's worse than a group of 5 where the weights are equal. But can we say something more about that? Like how much worse is this than a group of 5? Like is it the same as a group of 4 that splits its weights equally? Is it the same as a group of 3 that splits its weights equally? So we came up with this notion of effective group size, which is if you have some group with some distribution of social weights, can we say that its performance is equivalent to a group of some size that's democratic? So like some group of some size that like splits its weights equally, what does that size group look like compared to this one? And we want to do it for this particular distribution of social weights because that's what the experiment had. But in general, we want to see something like this. Like given any combination of social weights, can we map that to some effective group size? So I didn't know how to do it, so I started as small as possible. So I looked at a group of size 3, and you can map all of the possible combinations of social weights onto this simplex, where the vertices are where one bird has total control. So bird 1, bird 2, bird 3. The midpoints are where 2 birds have share control, and then the third bird has no control. And then the middle is where you have a democratic group. And so these points, you know what the effective group size is, right? Like if you're a dictator, then it's an effective group size of 1. If 2 birds share the decision, then it's group size of 2. And if it's democratic, then you have an effective group size of 3. And I would like to know what the effective group size is across the interior of this shape. But the only ground truth I have is for integer values of effective group size. And so I was curious to know what the shape of, like the isocline of effective group size of 2 is in this interior. Like we know it has to like touch these 3 points, but I didn't really know what the shape would look like. And thought that if I could simulate that shape, then I would have some information about what the functional form of the mapping would be. This is a math institute. Do you guys have a guess as to what it would look like? It's a circle. So the white line shows where the performance of this group of 3 is equivalent to a democratic group of 2. And then the blue is an effective group size less than 2, and red is an effective group size greater than 2. I feel like very self-conscious giving these slides at a math institute because like you will see I'm not that good at math. But I saw, I was like, oh, this looks like a circle. I think I know what the equation of a circle is. It's like the sum of squares. So then I like poked around and like guessed at the functional form for the equation of an effective group size, which is like some sum of squares of the social weights. Different birds might have like inherently like more or less information. So like I weighted each bird by the information, like the effective group size that it carries of its information. And then some inverse seemed like a reasonable measure of effective group size. But I wrote to Richard. He's going to help me out. Pretty sure this is right, but he's gonna make it more rigorous. But this functional form is like interesting because it shows up in a lot of places. So it's very similar to the Simpson diversity index, where you're measuring like the number of like species in a forest or something. In economics, there's an index to measure like how competitive an industry is, like is there a monopoly or not. In political science, you want to know like the effective number of political parties. So it all kind of like boils down to the same functional form. But to my knowledge, I haven't seen this specifically in the context of like collective decision making. So yeah, with this equation, you can do a lot of what I think are interesting things. So one, we can model the actual experimental condition from that paper. So this would be the effective group size of the next generation, would be a weighting of the experienced bird who carries the effective group size from the previous generation, and the weighting from the naive bird. So you can calculate like an infinitely long chain, like what would be the effective group size of an infinitely long chain. And then if the weightings are equal, like we found in the experiment, then the effective group size for an infinitely long chain of pairs is 3, which is not a very big number. So this says that an infinitely long pair, like if you took this experiment out to infinity, that infinitely long chain of birds would do no better than just a group of 3 birds flying together. And so again, go back to the data to see if that's true. So this is the plot that I showed before. But we can remap the x-axis or the y-axis from root efficiency to effective group size, again, by looking at the solo control flights and then just artificially combining them and averaging them. So this remapped. And I've highlighted effective group size of 5 because each chain of birds did have 5 birds, and then effective group size of 3, which I think is the asymptotic limit. And yeah, so the experimental birds had an effective group size of like 2.5, which is like pretty bad, in my opinion. Yeah, it's like interesting because so if the experimental birds had an effective group size of like 2.5, and they compared it to a pair control, which by definition is 2, then it seems like, I don't know, kind of lucky that they got a statistically significant result because it's just barely better than the pair control. So here I was calculating it, assuming that the 2 birds had equal social weights, but you can vary the social weights and look at what the sort of asymptotic effective group size is as a function of the social weight of the experienced bird. So at 0.5, it was 3, but if you give the experienced bird more social weight, then it can increase. But there's a potential cost to this. If you imagine that you're way out here, so your social weight of your experienced bird is really high, that means the social weight of the naive bird is super low. And so like every time you form a pair, you're only giving the naive bird like a tiny, tiny bit of weight, right? So it has like a tiny bit of influence. And so if there's like information accumulation from the naive birds, it's happening really slowly across generations. And that's true, and that happens, and that could be a problem. So here's examples of how effective group size increases across generations for 3 values here, where it's 0.5, 0.8, and 0.95. And I've also shown the asymptotic effective group size. So this tails off really quickly to 3. This one would tail off to 9. And this one eventually tails off to 39. But if you only get to play like 2 generations, then this blue strategy is really bad, right? Like if you can play infinite generations, then yeah, you want to be blue. But what the best social weight is depends on how long you get to play the game. And presumably, like homing pigeons and other animals have evolved based on what their typical situation is like. So it's like interesting to see what they do. So yeah, then I calculated, what is this? The optimal social weights as a function of how many generations you get to play. So if you play fewer generations, then you should have a lower social weights for the experienced bird. And then more generations, you should have higher social weight for the experienced bird. Which you can interpret as saying that if you don't get to play that many generations, then you just want to like get as much information as quickly as possible. And then if you're playing lots of generations, you want to prioritize not forgetting the old information. And because we empirically saw a social weight of 0.5, and that would be optimal if there's only 2 generations, then like maybe this suggests that pigeons like evolutionarily expect to be in like very temporary groups, and they're not expecting to like have these like multiple generations of information accumulation. Maybe. Let's see. Okay, so this was all pairs of birds. We can also model larger groups. Here I've just kept it simple and looked at democratic groups, so they split their social weight evenly. So here you can have a group size of n, and you decide to keep k of them in each generation, and then swap out n minus k of them. Whatever. The answer is the asymptotic effective group size is n plus k. Like these results are nice. They're so simple. It's like very pleasant to do. So yeah, but you face a similar speed accuracy trade-off here, where to maximize your asymptotic effective group size, you want to keep as many birds as possible and just swap out one bird per generation. But you're like accumulating information really slowly, so you have the same trade-off. It also could be interesting to interpolate between democracy and autocracy. So like those are extremes that we tend to think about when we think about sort of like the structure of animal groups. And it's hard to think about in-between cases because we just haven't really had a mathematical formulation for that. But this equation gives us that. So in this simulation, I assumed you have a group size of 20, and then you vary the social weight of one dude, and then you split the rest of the weight equally amongst everyone else. So if the social weight of that guy is over here, then it's like the same as everyone else, and you have democracy. But if you give that guy a social weight of 1, then you have a dictatorship. And then you can explore everything in between. So what I get from this graph is democracy is like kind of robust, but kind of fragile. Like this peak is pretty narrow. Autocracy looks pretty robust. Like even if you decrease the power of this bird by a lot, you still have like pretty bad effective group size. And then there's this, inflection points where you get a really steep decline in effective group size. And what's interesting to me is that this inflection point can occur really far away from autocracy. So this guy, goes from a social weight of 0.2 to 0.4, and you get this like collapse of effective group size, which means a collapse in like the performance, the collective decision making. Went pretty fast. Okay, so I think this is the last one. You can also look at the optimal social weighting. So if people come into the group with different amounts of information, like maybe it's a fission fusion group and they've learned different amounts about the situation and they now form a group together, what is the optimal social weighting given the amount of information that they have? And the answer here also turns out to be super simple. And this is just for a group of 2, but you can expand it out to any group size. And so this gives you a mapping between the quality of information you have and then what social weight you should use in your group. So this reminded me of what Ian asked Richard about, of like these models giving you like interesting experimental predictions that then you could test in games or whatever, where you could control the amount of quality of information for each individual and see like, do they learn social weights that make sense in a collective context? So to contrast the hypotheses of that original paper, which kind of like suppose that they need to have some ability to judge the quality of new routes and then prune the ones that are bad and preferentially keep the ones that are good. It seems like pigeons don't have any ability to do any sort of like complex sensing or like cognition or recognition or communication. They just seem to be simply averaging across the routes, regardless how good or bad they are. It increases the accuracy over generations, but it's generally pretty poor compared to other strategies that we looked at. But that's also partly due to the human designed experiments where it's like you have these pairs, and you swap out one. That causes a lot of the poor performance, which perhaps evolutionarily, this is like a weird thing for pigeons to experience. And yeah, they might be more optimal in the context in which they typically find themselves in. It seems like this idea of mapping groups with different kinds of social influence into an effective group size seems like a very useful way of characterizing the system and lets you calculate lots of interesting things and make lots of interesting predictions. So yeah, that was pretty short, but it's the last talk of the day. And yeah, I'm happy to take any questions.